All right, so now we can move on to electromagnetism. So we've done basically like quite a bit of module 5, right? So in terms of a summary of what we've done, we've looked at projectile motion, right? We need to know the two things: constant force downwards, and that constant force downwards is going to be gravity. No force horizontally, right? So no force horizontally. So that's projectile motion basics, concepts, I guess. The important thing about projectile motion is knowing the formulas and applying the formulas. In terms of getting good at projectile motion, I think because projectile motion is not very content based and very calculation based, I think a good way is just to get a lot of practice, so you have a lot of experience dealing with different types of questions. It's a bit different for other types of modules because more content heavy modules, there are different ways of preparing for them. But as you can see this through the summary that we went through, right? Yeah, the only main types of content that we really covered was LEO and GEO. There are some other stuff like Kepler's laws, which we won't get a chance to cover because we're not going to be going through every single detailed part of everything that we've covered so far, because lecture is only 2 hours long. But yeah, that is essentially module 5. Quick summary. And now that we've covered through module 5, we can move on to module 6. So we'll start with electromagnetism. So behavior of charged particles in electric and magnetic fields. So electric and magnetic fields so in terms of force, there's not much difference. They will both generate force, but they will generate different types of motion. So electric fields will generate parabolic motion, where magnetic fields will display circular motion. So what do I mean by that? Well, think about like an electric field, right? It will generate a force in a constant direction, right? So if an electron is traveling between a positively charged plate on the top and a negatively charged plate on the bottom, that electron will be attracted to the positively charged plate on the top. That electric field will generate a force upwards and a constant force upwards. So it will undergo parabolic motion, similar to the motion of a projectile in module 5, because we only have one constant force. In this case, it's upwards, whereas with projectile motion, it will always be downwards because of gravity. So that explains its parabolic motion. With a magnetic field, however, it's a bit different. So magnetic fields, you can say the force exerted by a magnetic field is always perpendicular to both the direction of the magnetic field and the direction of the movement, motion, or velocity of the charged particle. So this is for a charged particle entering a magnetic field. So if that is the case, then that means that the force will always be perpendicular to velocity. Where other case did we see that? Well, if I go all the way back, the only other case where we saw where force is always perpendicular to velocity, right? Let's assume blue to be force and red to be velocity. The only other case where we saw that is when we talked about uniform circular motion. So in this case, assuming that the direction of the magnetic field is perpendicular to the direction of velocity of the charged particle, the force will always be perpendicular to velocity as well, and so it will undergo uniform circular motion. It will start moving in a circle. So so it will start moving in a circle. So this particular example, the magnetic field will always point to the left. The palm will point out of the page, right? And the thumb will point upwards. So it will undergo uniform circular motion like this, essentially. Something like that, where it will move upwards initially and then curve downwards and then move upwards and then curve downwards. So undergo uniform circular motion. Again, tip 5, don't memorize the sine theta. Find the proportional velocity perpendicular to the B field. So again, these are where questions might trick people or attempt to trick people by trying to put in cases where sine theta doesn't apply and we'll have to look for cos theta. Basically, just think of it as finding the proportional velocity perpendicular to the magnetic field and not always sticking to the sine theta rule. In terms of the direction, right? So this one is going to be towards the oppositely charged plate. So if it's a positive particle, it will move towards the negatively charged plate. And if it's a negatively charged particle, it will move towards the positively charged plate. And that's because like charges repel and opposite charges attract. And then whereas with a magnetic field, we can use this, the right-hand palm rule, to calculate the direction of the charged particle. So what angle should we use in this formula? QVB equals sine theta, or QVB, F equals QVB sine theta, or QVB perpendicular. Well, we got to calculate the component of velocity that is perpendicular to the direction of the magnetic field. So if we use cos theta in this case, we'll calculate this component, right? That is parallel to the magnetic field. So in this case, we will be using sine theta because F equals QVB sine theta will be calculating this component. Sine theta will be this component, right? And so this component is what we're looking at because that is perpendicular to the direction of the magnetic field. So in this case, we'll be using sine theta. So a little bit more on the trajectories now. So this is also another place where you could be tested, right? Drawing the actual movement in electric and magnetic fields. I remember I got tested on this in my trials, or not trials, but one of my exams. I can't remember where, but we had to draw the motion of an electric field in between perpendicular charged plates. What's important is the electron will undergo like linear or straight line motion, and then the moment it hits this like electric field, it will start to undergo parabolic motion, so it will start to curve. And then the moment it leaves the electric field, it will once again undergo straight line motion because no force will be acting on it. And that's what's very important. You'll need to draw these with straight lines, right, before and after, and you need to indicate that it's very strongly that it is parabolic motion. The other thing is to be careful is always draw these lines equally spaced apart. So these field lines, always draw them equally spaced apart, and always with a ruler as well, obviously. And then in a magnetic field, it's a little bit different. Right, we have QVB is equal to mv squared over r. So we can find radius, we can find this. So by equating these and cancelling everyone, so we have QB is equal to mv over r. We can basically find different values based on what we're given. But yeah, it will just undergo uniform circular motion. So you can see here, the force is always perpendicular. The velocity, even though it's traveling in different directions, its plane will always be perpendicular to the plane of the magnetic field, which will in turn always be perpendicular to plane of the force. But yeah, now that that's out of the way, the different motions are out of the way, we can now move on to accelerating charges. So accelerating charges, as I mentioned before, create a magnetic field. Current-carrying conductors carry moving charges, and therefore current-carrying conductors must also create a magnetic field. So the way accelerating charges create magnetic fields is accelerating charges create a changing electric field, right? Changing electric fields lead to the or induce a changing magnetic field, which then induces a changing electric field, and so on and so on. And this is from our understanding of Maxwell and Maxwell's 4 laws. So an electromagnetic wave, essentially. So yeah, current carrying conductors must too create a magnetic field. So the direction given by the right-hand grip rule, right, and the direction given by the right-hand grip rule will be the direction of this magnetic field. So the direction of field lines will be in a circle like that. So we have the direction of current. So I'll point my thumb to the direction of the current, and then the way my 4 fingers circulate or grip will be the direction of the field lines. So that's what accelerating charges will look like in a magnetic field. And we can look at the motor effect. So what is the definition of the motor effect? Well, the motor effect states that current carrying conductor in a magnetic field will experience a force. Again, we have, don't memorize this angle, so we have a formula F is equal to ILB or BIL, whichever way you want to say it. But it's going to be perpendicular in the perpendicular direction. So we have sine theta added onto it. But don't memorize it to be sine theta, memorize it to be the perpendicular vector, or the perpendicular force. So yeah, because it could change from cos theta to sine theta. But with that out of the way now, we can look at parallel current carrying conductors. So this is the formula for force per unit length between 2 parallel current carrying conductors. So that is that formula. How to answer questions now. So what I would recommend is you guys draw dots and crosses to indicate the direction of magnetic fields if it seems confusing. If it doesn't, then you don't need to. But if these types of questions do seem confusing, then I would highly recommend drawing the dots and crosses to indicate the direction of magnetic fields and that are induced on one another, right? So the magnetic field that I2 will induce on I1 and the magnetic field that I1 will induce on I2. And this will really help with you guys determining whether this will pull or deflect other wires. So if we look at I1, right, it is, so I'll point my thumb upwards because it's going upwards, and my four fingers, right, they will go into the page. They will initially go into the page, which means that I1 will induce a magnetic field that goes into the page on I2, right? So if it's going into the page on I2, then to calculate the force, we can use right-hand palm rule, right? So we have the four fingers indicating the direction of the magnetic field that I2 is experiencing. So I2 is experiencing a magnetic field into the page from I1, right? And so my four fingers will go into the page. The current in I2 is going upwards, so my thumb will point upwards, and then my palm will point to the left. And so I have my red arrow pointing to the left. Same thing can be done from I2 to I1. So I2, my grip, so as my finger curves around, my fingers will leave the page, right? So as my finger curls around from my right hand grip rule, my fingers will leave the page. And so I2 will induce a magnetic field moving out of the page on I1. And so to solve this now, I will point my four fingers out of the page, my thumb upwards because current is going upwards in I1, and then my palm will point to the right. And so now I have a force to the right. And so this, a force to the left combined with a force to the right, indicates that when these two current carrying conductors are moving in the same direction, they will have an attractive force. So the force attracts. We can do a similar thing if they're moving in opposite directions. So what we'll do now is we will do the same thing essentially. So I2 now, right, to calculate the force the magnetic field that it will induce on I1, I will point my thumb downwards via right hand grip rule, and my four fingers will appear to go into the page. So I now have a force going into the page induced on I1 by I2. So to calculate the force that's induced on I1, I will do my four fingers going into the page and my thumb pointing upwards, and then I can see that my palm is facing outwards. So this is right hand palm rule, so my palm is facing outwards. And so I have a force going to the left. Same way now I can look at the force or the magnetic field that I1 induces on I2, right? The magnetic field that I1 induces on I2. So I resort to right hand grip rule first. So right hand grip rule, my thumb is pointing upwards. My grip, my four fingers can be seen going into the page, right? If it's going into the page, right? It's going into the page when my fingers are to the right of I1. I2 is to the right of I1, right? So fingers going into the page, that means a magnetic field going into the page is induced on I2. So then to calculate the force and the direction of the force, I will point my four fingers into the page, my thumb downwards because current is flowing downwards, and I can see that my palm is facing to my right. So I have a force going to the right. So I have a force going to the left and a force going to the right. And you can see over here that this kind of indicates that when my current carrying conductors are going in opposite directions, we have a repelling force. So that's what this kind of proves. And this is how you would prove it. You wouldn't be able to do the dots and crosses, right? But you wouldn't be able to do the grip rules. You can't physically call an examiner to test you on their grip rules. So what you do is you draw the dots and crosses that one would induce on the other one. So yeah, if you see dots, that means that they're going out of the page, right? So you can think about the arrow model, right? So you have that little cross or like the little, like, I don't know what to call it, those feathers at the end of the arrow, right? They look like a cross. So when an arrow is leaving you, you can see those little feathers and they'll look like a cross. So if they're leaving you, that you can imagine it going into the page, so you'll see like a cross. And if it's coming out of the page towards you, then you'll see the little point of the arrow, right? So you'll see dots. So that's the arrow method. So yeah, dots out of the page, crosses into the page. All right, so let's look at this 2013 HSC example question now. So P, Q, R are straight current carrying conductors. Conductors P and R are fixed and unable to move. Conductor Q, on the other hand, is free to move. In what direction will conductor Q move as a result of the current flow from conductors P and R? So if you think about this, right, we thought, or like, you know, we formulated earlier, or we found earlier, that when they're in opposite directions, right, when the so comparing Q and R now, when the current will travel in opposite directions, there will be a repelling force. So R will induce a force to the left on Q. That's the only way it can be repelled from R, right? And we also found that if current carrying conductors travel in the same direction, so P and Q now, they will induce, or they will result in the induction of an attractive force, right? So P wants Q to come towards it, and R wants Q to go away for it. So this kind of indicates to us that Q, the direction, will be to the left, and both of them will generate a force in the same direction, right? So how we solve this question? Well, first we'll draw the dots and crosses, and we'll calculate the direction the given conductor will move in. So drawing the dots and crosses now, we can see that R, right? R, if I do my right hand grip rule, it will produce 4 fingers will go into the page, and we have green crosses going into the page. Green crosses going into the page. Whereas with P, we will have P again, it will go into the page. So we'll have pink crosses as well. So we have green crosses representative R, and pink crosses representative of P. And so P and R will both result in magnetic fields going into the page. So we have crosses in both cases. You guys can ignore blue, but blue is representative of the magnetic field that Q would generate, but that's irrelevant in this case because P and R are stationary, and Q can only induce forces on P and R. It can't induce forces on itself, right? But P and R can induce forces on Q because Q is free to move. So it will generate like motion. So in this case, both of them are into the page. So we see crosses from both P and R. So what is the force then on wire Q? Well, to calculate the force, so this will be looking for like a numerical value, right? So to calculate this force then, we can use the formula that we went through a bit earlier. So this formula, F over L, right? So we have L, 1 meter. So it's pretty, and we have the distance, right? 5 and 2.5. So we have R as well, and we have the currents as well. So we have I. This is a constant. This constant is given to you on your data sheet, mu naught. So yeah, knowing everything, we can now plug everything in now. So current flow in the same direction equals attract, in the opposite direction equals repel. So F over L is equal to mu naught over 2 pi times I1, I2 over R. This constant is equal to 2 times 10 to the power of negative 7. It doesn't change because it's a constant. So now we can go ahead and calculate the force between PQ. PQ, we have 2 times 10 to the power of negative 7 times 6 times 2 times 1. This 1 comes from L, which is just 1 meter. Right, 6 times 2 comes from the currents, 6 and 2. And then we divide it by 5 times 10 to the power of negative 3 because they're separated by 5 millimeters. And that yields us a force of 9.8 times 10 to the power of negative 4 newtons, negative 4 newtons left. And then we can calculate the force between R and Q. So again, we have the constant 2 times 10 to the power of negative 7 times 2 times 2 times 1. We do 2 times 2 times 1 because Q has a current of 2 and R is a current of 2. So we have 2 times 2 times 1, and that is all divided by 2.5 or times 10 to the power of negative 3 because they are separated by 2.5 millimeters. And that yields us a force of 3.2 times 10 to the power of negative 4 newtons left. So because they're both left in this case, we can just add them together and we'll get a total force in Q of 8 times 10 to the negative 4 newtons left or towards P, whichever way you want to say it, but they will both indicate the same direction. So yeah, that's how you would solve those types of questions. Knowing that, now we can move on to electromagnetic induction. So electromagnetic induction is when a conductor exposed to a change in flux induces an EMF, right? A conductor which is exposed to a change in flux induces an EMF. So then the key question is, what is flux? So flux is basically how many lines are going through an area. And flux density is how packed these things are. So flux can be the same. So in this case, right? In this case, flux is the same. You have 4. Flux density, however, is not the same because the area has increased, whereas we still have 4 crosses. So flux is the same, whereas in this case, flux density is not the same. So that's something that you guys should keep in mind. So those two things can be different. So now we can, knowing this content, now we can move on to Faraday's and Lenz's law. So definitions, these two are highly important, and I would recommend that you guys know them by heart, because I recommend that whenever you guys do a question that involves EMF or back EMF or something, always write down Faraday's and Lenz's law so you can come back to them and refer to them when you're doing your explanations. So Faraday's law states that relative motion between a conductor and a magnetic field induces an EMF. And Lenz's law states that this induced EMF will create a current in a closed circuit and generate a magnetic field that opposes the change in flux. So that's Faraday's law and Lenz's law. Lenz's law is like it will generate a B field that opposes change in flux, and Faraday's law basically says it will induce an EMF. So all right, so let's look at the conservation of energy now. So what is the law of conservation of energy? Well, the law of conservation of energy basically states that energy cannot be created or destroyed. It can only be transformed from one form to another. So it can only be transformed or transferred. So DC motor example then. DC motors, they produce back EMF. Back EMF opposes the supply EMF, right? Why doesn't it support the supply EMF? Well, if it did end up supporting the supply EMF, then that would mean that we'd have more current, more torque, and so the rotor would spin faster, and then the coil will experiences a greater change in flux, and so we'll have more induced current, more torque, more, and they will just keep repeating, and then we'll end up just getting infinite energy. Like, if it did support the change, right, all I'd have to do is just like to power this like nuclear plant motor, I just have to plug in like one AA battery, and eventually the motor will start spinning and supplying its own like EMF, right? That obviously violates the law of conservation of energy because it kind of indicates that we are creating energy, when energy cannot be created or destroyed, only transformed or transferred from one form to another. So back EMF is like an opposing force to supply EMF, always opposes. So let's go through a recap of solenoids now. So fingers point in the direction of the current, the thumb point in the direction of the North Pole. So if your solenoid is in this case, right, if your solenoid is pointing upwards, your fingers will point upwards, like they will curve along with the direction of the solenoid, and then whichever direction your thumb points in will be north. So yeah, little recap of solenoids. We can move on to the definition of eddy currents now. So eddy currents, what are they? Well, eddy currents are circular induced currents set up when bulk pieces of metal experience a change in flux. How would you determine the direction of these eddy currents? Well, these eddy currents will act to oppose the initial change in flux following Lenz's law. So if you look at this example, right, I have a North Pole, and let's say I have a sheet of metal, right? So let's explain its motion is moving this way. So let's say it's moving right, right? Right, so if it's moving right, that means that, so we have magnetic fields going downwards, right? If it's moving right, that means that this part of the metal, right, this like small section of this metal, right, is experiencing a change in magnetic flux. What is that change? That change is that it's going to go from experiencing a magnetic field to not experiencing a magnetic field, right? So it's the field lines going into the page are decreasing, right? So what it wants to do is it wants to supplement this. It wants to oppose this feature, right? It wants to oppose this change, resist this change by basically supplementing it by providing its own magnetic field lines downwards. And that will kind of resist the change and make it harder for us to pull the sheet out. How will it do that? Well, it can generate a current circulating in this direction, right? And that will generate a magnetic field line slash magnetic field basically going downwards, right? Via the grip rule, generate a magnetic field going downwards, right? So it kind of supplements that force. Sorry, it supplements the change in magnetic flux, right? It opposes the change in magnetic flux. It opposes the change that it's experiencing, right? With the changes, it's lowering in the amount of magnetic field lines cutting through it. So then to oppose that change, it will kind of induce its own magnetic field in that same direction, right? And then let's look at the other side. So the other side is going from having no magnetic field to then all of a sudden being dragged into a magnetic field. So then this other side will try to oppose its change in the opposite, like in an opposite way. So it will try to minimize the impact that this magnetic field lines will have on it by generating or inducing a magnetic field that goes in the opposite direction to counteract the magnetic field from this North Pole, right? Because it initially didn't have any magnetic fields. And so it doesn't want to change. It wants to oppose the change. And so in this case, it will generate an eddy current going in the opposite direction to generate a magnetic field upwards. So the basis of everything is it will always try to oppose the change. So in this side, it doesn't want to leave the magnetic field because it was initially in the magnetic field. And so it will generate a current in this particular manner. Whereas on the other side, it wasn't initially in a magnetic field, but now it's being dragged into a magnetic field as this sheet of metal is being dragged along. And so it wants to resist its change by inducing a magnetic field in the opposite direction. So eddy currents will always induce magnetic fields, but its direction is determined by, does it want, like, is it losing out on a pre-existing magnetic field, or is it being introduced to an existing magnetic field? So that's what determines or differentiates between the different directions. That's what we can use to determine the two different directions. All right, so let's look at this question now. What direction is the current induced in the ring as the magnetic field is turned off? So let's see what happens when the magnetic field is turned off, right? What will happen is we will initially, so within this magnetic field itself, right, we initially have magnetic field lines cutting across it going into the page, right? Because we see crosses into the page. And then all of a sudden we turn it off. So all of a sudden it already had magnetic fields going into the page and now it doesn't, right? So it wants to oppose the change by having its own magnetic field going into the page. So it can feel like it was in its magnetic field originally, if that makes sense. So originally it was already in a magnetic field. We turned it off. So that was the change. We removed the magnetic field. It's going to try opposing that change by inducing a similar magnetic field in the same direction. So this one will try and induce a magnetic field in the same direction by going into the page, right? So it will induce a magnetic field going into the page. To generate that, I will point my thumb into the page and I will see in which direction my fingers turn. My fingers turn clockwise, and so I will induce a current in the clockwise direction. And this will induce a magnetic field going into the page, which will be the way of opposing the change that it's experiencing, if that makes sense. So that is that particular example right there. We can now move on to electromagnetic braking, which is an application of our understanding of electromagnetic braking, which is an application of our understanding of eddy currents. So this is kind of what it will look like in a car or a train or wherever electromagnetic braking is used, right? So so we have an electromagnet that can be turned on or turned off. And when we want to brake, we'll turn the electromagnet on and we will kind of induce this magnetic field on it. This will generate eddy currents, right? And so those eddy currents will try and oppose the change in magnetic flux. And what ends up happening is it'll end up generating a force that will oppose the change in motion that we're doing. So because the magnetic field will oppose the change that we're doing, the force generated will also oppose what we're doing. So if we're trying to turn it this way, it will kind of slow it down because the force generated will be resistive. So they will turn in different directions, right? Because so in this direction, right? If we're looking on the side facing towards us, right? Let's assume the magnetic field is coming out of the page, right? If we're turning the wheel anti-clockwise, then this side of the wheel, right, will be leaving the magnetic field. It doesn't want to leave the magnetic field, right? So it wants to oppose this change by inducing its own magnetic field in the same direction. So it will induce a magnetic field, right? It will induce an eddy current going anti-clockwise. That will induce a magnetic field going out of the page. So the eddy currents on this side of the wheel, on the left-hand side of the wheel, will be turning anti-clockwise. If we look at the right-hand side of the wheel now, this part of the wheel now is being, as it's turning, right, it's being introduced into the magnetic field. That's also a change. It doesn't want to be introduced into a magnetic field because that will change magnetic flux, right? It doesn't want to change. It wants to oppose the change. So to oppose the change, it will try to generate a magnetic field in the opposite direction to kind of counteract it or to balance it out, right? So it will now turn clockwise, right? It will turn clockwise to generate a magnetic field into the page, right? Because it's being introduced into a magnetic field coming out of the page. So it will generate a magnetic field going into the page in the opposite direction, sorry. And so eddy currents on the right-hand side of the wheel will turn clockwise, whereas eddy currents on the left-hand side of the wheel will turn anti-clockwise. So yeah, that is eddy currents. All right. So now, so how it works basically is we have a change in EMF, and then it results in an induced back EMF, and then the speed decreases because there's a force applied. In terms of electromagnetic braking itself, there are a couple advantages to normal braking. Electromagnetic braking can also be called regenerative braking as well, because we can use this induced back EMF to kind of charge the battery in the car, if that makes sense as well. So, or we can use the eddy currents to charge the battery. So, let's think about the way advantages and disadvantages of electromagnetic braking. So if you look at this picture, right, as you can see, the electromagnet isn't touching the wheel isn't touching the electromagnet. It's just basically the wheel by itself, right? So electromagnetic braking doesn't require any parts in contact, right? It doesn't require any parts in contact. The electromagnet can be stationary, the wheel can be the only thing moving. And that is an advantage because you won't damage things based on them being in contact and rubbing against each other and becoming loose and stuff. You won't have that. But then a disadvantage is, and another advantage is in terms of sound, I guess. You won't like with trains braking and stuff, you'll hear a lot of sound and stuff, but of the moving parts, right? In this case, you won't. But a disadvantage at the same time is you'll generate a lot of heat, right? Eddy currents cause energy loss due to heat, right? And so there will be a lot of heat produced depending on the scenario. So if it's trains, right, they're very heavy and there's lots of brakes on it, it will generate a lot of heat. And that could themselves wear down the materials. So there's an advantage, and it's also a disadvantage compared to normal braking that we have. All right. Now let's look at transformers. So, what is a transformer? Well, a transformer is a device that increases or decreases the voltage of an alternating current. It has to be alternating current because transformers need a change in magnetic flux to do what it does. So, it either increases, steps up, or decreases the voltage of an AC current. So we have a first coil and we have a second coil, and there's basically magnetic induction is what occurs. So we induce a voltage in the second coil from the first coil. And this can be better done through a core, but in this case, this transformer doesn't have a core. So there are a couple of things that affect the efficiency of a transformer. A couple of things. So first of all, we have eddy currents. And as I mentioned before, right, eddy currents cause energy loss due to heat. And so these transformers could have very low efficiency due to energy loss due to heat. We also have flux leakage. So flux leakage is where the magnetic flux isn't fully transferred from the primary coil into the secondary coil. That also leads to changes in efficiency because we're not fully transforming the energy from the primary coil into the secondary coil. Some of it's lost, right? So that also affects efficiency. In terms of what we can do to improve these types of efficiencies, well, with eddy currents, what we can do is we can laminate the core. Laminating the core with this is an example of eddy currents by themselves in a non-laminated core, and this is an example of a laminated core. As you can see, the size of eddy currents are a lot smaller, and so because of that, the heat loss or the energy loss due to heat that they will cause is a lot less. So laminating the core is a good way of mitigating this issue. In terms of flux leakage, couple things that you can do, right? Obviously, if I had a core, there will be a lot less flux leakage. As you can see, the lines are a lot more aligned, right? The magnetic flux, as opposed to without a core. So obviously, the first thing that I would do is have a core, right? Have a core, and also make sure that this core is made out of ferrite. Right, ferrites are things that are electrically non-conductive but magnetically inductive, which means that they'll minimize the formation of eddy currents. Right, minimize the formation of eddy currents because they're not very electrically conductive, but they will be very magnetically conductive, and so you have very little flux leakage because they'll be very conductive to magnets essentially. So yeah, that's that. So yeah, note that the equation Vp Vi equals Vs Vi assumes perfect efficiency, right? If you don't have perfect efficiency, then Vp Vi will be equal to, like, say you have 90% efficiency, then Vp Vi, right, the power in the primary coil will be equal to the 0.9 times the power in the secondary coil if you have 90% efficiency. So Vp Vi or Vp Ip is equal to 0.9 VSIS. All right, so let's look at now an AC induction motor. So this is also like a complex area of module 6, I could say. So an AC induction motor consists of a squirrel cage rotor, 3 sets of stator magnets at 120 degrees from one another, and an axle. So this is kind of what it looks like, right? First phase, second phase, third phase. Yeah, they have 3 phases. If you look at in the factories and stuff, they often target 3, or they often intake 3 phases. Households and general stuff like that, we only intake 1 phase. But yeah, AC induction motor, right? How it works is the 3-phase AC current creates a rotating magnetic field. So we induce a magnetic field here, then here, then here. So it kind of induces or creates a rotating magnetic field, right? And this rotating magnetic field will cause the field lines to cut through the squirrel cage rotor, and so there will be cutting of magnetic field lines, and so we can say that there will be the squirrel cage rotor will experience a change in flux, right? So to minimize this change in flux, it will try and rotate in the same direction as the rotating magnetic field to basically try to minimize the cutting of magnetic field lines, as it says. So if the magnetic field lines rotate in this direction, then to minimize the change in magnetic flux that the squirrel cage rotor will experience, it will also turn in that same direction, right? But it will never catch up, because if the squirrel cage rotor catches up, that basically means that the squirrel cage rotor has 100% eliminated the input energy that we put in to rotate the magnetic field. And that also violates the law of conservation of energy, right? So the squirrel cage rotor will always be a little bit slower than the rotation of the magnetic field, or the rotation speed of the magnetic field, sorry. And therefore, the squirrel cage rotor will always experience a change in magnetic flux, and because it will always experience a change in magnetic flux, it will always keep rotating, assuming we keep the magnetic field on. And so the difference between the rotational velocity of the magnetic field and the rotational velocity of the squirrel cage rotor is referred to as slip speed. So that might be some, if you see that word in one of your exams, that is what it means, slip speed. All right, so let's look at applications of the motor effect now. So what applications of the motor effect are very evident in motors, right? Essentially, we're placing a coil in a magnetic field, and as we pass a current through it, it causes it to turn, and we can use the right-hand rule to figure out the direction of motion, right? So the important thing with motors is you need to differentiate between slip rings and split ring commutators, right? So AC uses slip rings because AC current is already alternating, so we only need these slip rings to ensure that the coil is always connected to the circuit. So these are the slip rings. And with DC, however, we use split rings as well. Split rings make sure that we change the direction of current every half turn to keep the motor moving in the same direction. So we can say To preserve unidirectional torque, split ring commutators change the direction of the current in the coil every half turn. To preserve unidirectional torque, which means torque in one direction or one direction of rotation. So yeah, and these are the split ring commutators in a DC motor. Always remember, DC motor split ring commutator, AC motor slip rings, because slip rings don't alternate the direction of current because AC current is already alternating. So yeah. We also have now generators, which kind of do the opposite of motors, right? Motors, we input energy to cause it to turn. Generators, we turn it to generate energy. So yeah, it's basically like a reversed motor. So same kind of setup, except we supply an external force to turn the coil, and that will generate an induced EMF, an induced current, and that induced current is what we're harnessing to generate energy, basically. And examples of these include wind turbine blades, and also like steam powered like factory blades and stuff as well.